Okay, I think the recording has started. Okay, so welcome back. So we will actually start with the lecture directly this week and probably do the announcements after break. So let me share my screen. Okay, so maybe before we begin, let's quickly recap what we did in the previous lecture. Sorry, yeah. So we spent a lot of time last week in linear classification. So we started with like 3 different approaches for doing classification, like which are either generative approach or discriminative approach or discriminant based, right? Like, and then like we focused in the previous lecture on the geometry of linear decision surfaces. So to summarize what we discussed, like, so I think it could be summarized by this one picture. So essentially, like we wanted to understand the linear model for classification, which is y of x is equal to w transpose x plus w0, right? So now we had like 3 observations. So specifically, like what is the role of this w, what is the role of this w0, and what does this y, the value of y means, right? So if you remember the 3 observations, W basically decides the orientation of the decision surface, right? Like, so we found that W is actually perpendicular to the decision surface. And then the W0, like we found that W0 decides how far is this decision surface from the origin, right? So in some sense, it decides the displacement of the decision surface. And then Y of X, which is a value or a score for X, tells you like some signed value of like how far is this data point X from the decision surface, right? So this was like, this is the summary of like what we have seen about linear decision surfaces in like in the case of a 2-class classification problem. Okay, so now in today's lecture, as a first step, we are going to extend these intuitions to multiple class setting. Okay, so now instead of having 2 classes like in a binary classification setup, let's say we have k classes. Okay, so when you have k classes, like how do we come up with decision boundaries, right? So there are many ways to do this. So we will look at each of them and discuss like when you can apply those things and like what are the limitations. So the first approach that we are going to see today is one versus the rest classifier. Okay, so the idea here is if you have, let's say, 3 classes, for every class, you create a decision boundary. And this decision boundary is going to tell whether the example belongs to this particular class or not. Okay, so for example, let's say I have 3 classes, C1, C2, C3. Okay, so remember that in the case of 2-class problem, if you just have C1 and C2, all you need is a line, and this line is going to say, okay, this part is C1, this part is C2, right? So then we are done, right? But in the case of 3-class problem, how are we going to use these linear decision boundaries and still do a multi-class classification? So the first approach is one versus the rest, where like you would have one classifier which tells whether it belongs to class C1 or not C1. Okay, so it's going to classify everything else like C2 and C3 as not C1. Okay, similarly, you could have another classifier, okay, which is going to say this is class C2 and this is not C2. Okay, since we have only 3 classes, if something is not C1 and not C2, that is going to be C3, right? So this region is basically C3. Is that clear? Now, this approach has a small issue, which is basically this decision surface, like the region, right? So in this region, everything is classified as both C1 because it's to the left of right, like red color, right? And also as C2 because it's to the right of C2, decision boundary, right? So now this is the issue with one versus rest classifier, okay? Okay, so can we do better than this? So there is a second approach, which is basically one versus one classifier. Okay, so in this case, instead of having, okay, remember that like in one versus rest, if you have k classes, you're going to have k minus one decision boundaries, right? Like, or in some sense, k minus one binary discriminant functions, right? So now the next approach is one versus one classifier, okay? So in the case of one versus one classifier, instead of considering k minus one classifiers, we are going to consider like k into k minus one by two like binary discriminant functions, okay? So the idea here is you're going to come up with one classifier for every pair of classes, okay? So if you have C1, C2, C3, you are going to have C1 versus C2 as one classifier, okay? Then C1 versus C3 as another classifier, C2 versus C3 as another classifier. Okay, well, in this case, since it is only three, since it's like three classes, like you have only three decision boundaries, but like as you can see from the formula, like if you have more classes, you are going to have like way more decision boundaries, right? Like, so now how does this classifier work? Like, so like would the decision function of this classifier would look like? So for example, let's say this is the decision boundary for C1 versus C2. Okay, and similarly, let's say this is the decision boundary for C1 versus C3. Okay, so now anything in this region, right? So this region is called the region for class 1. Okay, now similarly, I could have the third classifier, which is C2 versus C3. So let's say this is C2 versus C3. Okay, so now you can see that this region, right? The region in the bottom is for class 2, and this is for class 3, okay? And maybe I would just highlight, so I would, okay, so yeah, this is fine. So I would just highlight the fact that, oh, sorry. This whole region is R3, right? So similarly, I would also remove this. I would also remove this. Like when you do majority, it's this whole region is R2. Similarly, this whole region is R1, right? So now the problem with this type of classifier is this region, the middle region, right? So this middle region is classified as, like, from this side it's classified as C2, from this side it's classified as C1, and from this side it's classified as C3, right? So it's classified as all the three. So this is the region of confusion for one versus one classifier. So normally in one versus one classifier, you're going to have a bunch of classifiers like pairwise, and then you take a majority voting. So see how many times C1 is predicted, how many times C2 is predicted, how many times C3 is predicted, and take the majority. Okay, is that clear? Okay, so now this also has some issues, right? So there's actually a question. So do we use one versus the rest since it has this issue? I will answer that like once we see all the three ways of doing multi-class classification. So the final approach that we are going to consider is like we're going to consider a single k-class discriminant, okay, comprising k linear functions of the form yk of x is equal to wk transpose x plus wk0. Okay, so what am I doing here? So in this case, like instead of having different decision boundaries like 1 versus rest or 1 versus 1, I'm just going to consider k discriminant functions. If I have k classes, I have k of these y's, okay? And the way in which I'm going to do classification is if yk of x is greater than yj of x, for all j not equal to k, then x belongs to class k, class ck. Okay, so this is a bit different from the previous two classifiers, right? Like in this case, I generate k different y's, like some values, right? Like and see which one of them is the largest, and that is the class for this particular x. Okay, so now how would the decision boundary for such a function would look like? So the decision boundary between, let's take two random classes, ck and cj. Okay, so the decision boundary in this case is the point where yk of x is actually equal to yj of x, right? Because if yk of x is greater than yj of x, then that belongs to class k. And if yj of x is greater than yk of x, that it belongs to class j. And the middle point, like where both the values are same, is the decision boundary. Okay, so now we can expand this. So yk of x is given by wkx plus wk0, and yj of x is given by wjx plus wj0, right? So I can do a little bit of rearrangement here, and it becomes wk minus wj transpose x plus wk0 minus wj0 is equal to 0. Okay, so now you can see that this equation of the decision boundary is actually very similar to the decision boundary in two-class setting, right? So this is very similar to the two-class decision boundary that we discussed in the previous lecture. So in some sense, all the geometrical properties that we have discussed in the previous lecture applies for this third way of doing multi-class classification. Okay, so this is better than the previous two approaches, simply because the decision regions of such a discriminant are always singly connected and convex. Okay, so what do I mean by singly connected and convex? So this particular like way of doing multi-class classification does not have the confusing regions. So if you have three classes, your decision boundary would look something like this. So where this is some class Ri, this is some class Rj, this is some class Rk. Okay, so I call it singly connected because like everything of one region, right? Like so it's together, right? And this is convex. So what do I mean by the fact that this is convex? So you take any two random points, xa and xb. Okay, now you consider the line between these 2 points and find any point in between. Let's call this as x hat. Okay, so if xa and xb has the same class, then x hat should also have the same class. Okay, so any point x hat that lies on the line connecting xa and xb like we can express that as xa is equal to some lambda times xa plus 1 minus lambda times xb for 0 less than or equal to lambda less than or equal. So this is the equation for x hat, right? Like x hat is some combination of xa and xb. So let's just call it as lambda times xa plus 1 minus lambda times xb, right? Now, if I do yk of x hat, that's going to be equal to lambda times yk of xa plus 1 minus lambda times yk of xb. Okay, now this is by linearity of the discriminant. So we are dealing with linear discriminant functions, so you can just like directly apply the y inside, and this is by the linearity. Okay, so we already know that yk of xa is greater than yj of xa, right? And so these are points in the kth decision boundary, right? So yk should be the maximum when compared to yi, yj, yk, right? So yk of xa is greater than yj of xk. Similarly, yk of xb is greater than yj of xb for all j not equal to k, right? So now this basically means, so this term is greater than all other j terms. This is also greater than the j terms, right? Like similar. So this means this should also be greater than. So like another way to put this is like yk of x hat is greater than yj of x hat for all j not equal to k. So this means that x hat belongs to Rk. Okay, so thus Rk is singly connector and convex. Okay, so as a summary, like we have seen three types of like three ways to extend the linear discriminant functions to multi-class classification, right? Like, so we looked at one versus the rest, and we saw that, okay, there is some issue, like you cannot do this all the time because there might be situations where you might get confusing predictions. Similarly, one versus one classifier, which also has some issues, right? So the most common way to do multi-class classification is by using this idea of k-class discriminants. So where like you just have k discriminant functions, and the boundary is given by when two class values are together, right? So, and the class prediction is decided by finding which y has the maximum value, right? And we also saw that this specific type of multi-class classification is interesting because you don't have like the issues like the previous two methods, right? Like, so in this case, the decision boundary is actually singly connected and convex, which means every x has a unique value for prediction. Okay, so maybe I would take a few questions here. So now I think that answers some of the questions in the chat. So normally the third option is preferred. But sometimes, like when you have to deal with binary classifiers to come up with multi-class classifiers, then you have to use one of the previous two approaches. Okay, so then there is another question in the chat, which is for most J, but not for all of them. Okay, so the question is, what is the classification of X if yk of x is greater than yj of x for most j but not for all of them? Okay, that is not possible, right? Like there is always a maximum value. So if you don't, if there is, okay, so well, there is always a maximum value, but sometimes, like let's say two classes have the same value, then it is a tie. So you break the tie by randomly picking one of those two classes. But that is very rare simply because you're dealing with real numbers. So like even like to a decent precision, like so you would always have a maximum. But it's not it's not impossible that like you have a tie. When you have a tie, you just break the tie. Okay, so any more questions or hand raises before I move on? Okay, so there is, okay, so 1 second. Lawrence is here. I want to make her a co-host so that, okay. Okay, I made her a co-host. So what's the relation with cross entropy? We will see that very soon. Okay, I haven't introduced cross entropy, by the way. So like when I introduce that, like we will see the relation. What if yk and yj are parallel? Well, that will not happen in this case. So that is exactly what the final short proof that we did tells us. It says that the decision surface is going to be singly connected and convex. So this is the structure. Okay, so now let's continue. So now that we have done a lot of geometry to understand the decision surface, let's actually go back to the least square classification model that we had. Okay, so now this time we have, like we are equipped with more intuitions, so we can actually see like what is least squares actually doing for classification. Okay, least squares for classification. Okay, so let's consider that I have a k-class classification problem, k classes, okay? And we need a way to make the classes as numbers, right? So we have already seen in the previous lectures that you could do 1 of k binary encoding, right? Or the other way to say that is like one hot encoding for the classes. Okay. Okay. So now we have a one hot vector that we are trying to predict, right? Like for class, let's say for simplicity, let's say I have C1, C2, C3. The one hot vector for C1 is given by 1, 0, 0, right? For class 2, it is 0, 1, 0. For class 3, it's 0, 0, 1. This is what we are trying to predict, okay? So now we already know that if you're doing least squares, the optimal prediction in least squares is the expected value of t given x, right? So least square is trying to predict the conditional mean, right? So now knowing this, it makes more sense to use least square for classification with such a one hot encoding, simply because in some sense, this one is the probability of class 1 given x, right? So the 0 means the probability of class 2 given x. If you are dealing with class 1, the probability of class 2 is 0, right? Similarly, class 3 is 0 and so on. So this like the moment we start using one hot encoding and the fact that least square is actually trying to model the conditional expectation, right? So specifically for this binary coding scheme, okay, so it makes sense to use least square. Okay, however, there is a problem here. In the case of least squares, it is just a linear model, right? So the y can take any value that it wants to take, right? Like, so in some sense, it's like a discriminant and it produces a y, and the y could span the entire line, right? On the other hand, this particular classification problem takes only two possible outputs, either 0 or 1, right? Like, or something in the range of 0 to 1, right? But we don't have that guarantee with least squares. So with least squares, there is no guarantee for the values to be in 0, 1 range. Okay, so now this is a problem, right? So for each, like if you're using least squares for multiple classes, like then for each class, you're going to have yk of x is equal to wk transpose x plus wk0, right? Like for k is equal to 1 k, right? So now I'm not going to redo the whole derivation for least squares, but if you do the derivation, then you would see that the solution w hat is given by x hat plus transpose, where this x hat plus is the pseudo inverse, right? X transpose, X inverse, X transpose Y, but in this case, Y is T, the target for the classification, right? So we have done this probably multiple times, right? So we are not going to rederive least squares now, but I just want to end this discussion with a couple of notes. So the first note is, if every, this is actually a very interesting note. So if every target vector in the least square model prediction, like let's say every target vector in the training set satisfies some linear constraint. Okay, so let's say some linear constraint a transpose t power n plus b is equal to 0. Okay, for some constants a and b. Okay, then the least square model for any value of x will also satisfy the same constraint. Okay, so if my training data has such a linear constraint, then the model that I am learning will also have the same constraint. Okay, so now what is the constraint that I have in this particular one-hot encoding? So this is my target, right? And you can see that in the case of this specific binary encoding target, all these targets should sum up to 1, right? So I have 3 y's that I'm predicting, 1, 0, 0, so it sums up to 1. 0, 1, 0, it sums up to 1, right? So this is the constraint that this particular classification problem has. And I would encourage you to go try doing least squares for classification, and you would see that the output of this model will actually sum up to 1, okay? But the point to remember is it just sums up to 1, but it can take any negative values, right? So it's not like it's a probability value. It is still some real number which could also be negative. Okay, so that's the first interesting note. Second note is probably the limitations of using least square is least square solutions lack robustness to outliers. Okay, so what do I mean by that? So let's say I have a bunch of data points, crosses, and circles. Okay, so I have to draw a line to classify these two by using least squares, and roughly this is what the classification boundary is going to be, right? Okay, so I can easily shift this boundary by just adding few more circles, but far away from the original distribution. Okay, so probably these 4 data points that I have here, right, these could be outliers because all the circles stay in the same place and there are only 4 examples which are far away, right? So these could be outliers, but the least square solution would actually consider these data points, and hence it's going to change the decision boundary. So let me draw another decision boundary. So it's going to change the decision boundary, and maybe it will go something like this because it also considers and it gets pulled by the outliers. Okay, so if something is too correct, in some sense these outliers are too correct, right? Like, so they, even with the previous red decision boundary, they are perfectly fine, right? Like, so they are below the red line, so they're going to be circles anyway, right? Even when they are correct, like since they are too correct, like so linear, like linear regression based classifier or least square classifier is going to change its decision boundary and hence have bad decision boundary. Okay, so this is the problem with least square. Okay, and one final note is it doesn't work well in many places, as you would assume. This is the first simple classifier that we have learned. Like, we are going to look at many more better classifiers, but here is an example of a 3-class classification problem where I'm doing least squares. and you can see that the green is not classified properly at all, right? Like, so most of the green is classified to either red or to the blue, and there is actually this very small region which is given for green, right? Like, so in some sense, it doesn't work well in many cases. Okay, so in the future, like, we would actually see better classifiers than least squares. Okay. Okay, so I think that concludes our discussion on linear classification. So now we will probably move to the next chapter in the notes, but maybe I'll take a couple of, I'll just take the questions in the chat. So can't we just delete outliers? Okay, Krunal, I will let you answer, ask your question after answering the chat. Okay. Can't we just delete outliers before applying least squares? Yes, that is a good practical approach. So normally, like, you would do some outlier detection and remove those outliers and then run your algorithm, so that, like, it's like, especially if your algorithm is not robust to outliers. Okay, if the constraint is that the sum is equal to 1, doesn't that mean the output vector will also be equal to 1? Then we don't have the problem that, okay. Emmanuel, to answer your question, the constraint that we have in this classification problem is like the sum is 1, right? But sorry, the sum is 1, right? Like, but y is just a real number. It need not be always positive. It could also be negative, right? So if it is also negative, then, like, we don't have the guarantee that they all like sum up to, like, even though it sums up to 1, they don't have the probabilistic interpretation. Okay. Maybe Krunal, you can ask your question.
Hi, yeah, I still have the question in that same reason. Can you go back to that previous slide?
Okay. This or even back?
Yeah, where you have stated that note 1.
Okay. Yeah.
Yeah, so if all the points are satisfying a linear constraint, then the output, the model would also satisfy the same linear constraint, right?
Yes.
That's what it says. So
Yeah.
so you just said that it means that every y where respect that sum is equal to 1, but then
yes,
all the points are also satisfying that individual component is either 1 or 0. So wouldn't that also satisfy
well,
that the
no,
value
that
should
is
go negative
no,
or
but
the
that
value
is
should
not
go
the
above 1?
no, but that is not the linear constraint that you have at the output level, right? So the only linear constraint that you have at the output level is, like, they should sum up to 1, right? So they could also, for example, they could also sum up to 1 by 5, I don't know, -5 and 1, right?
Okay, so
So this
it's a
happens.
constraint only on the
Yeah.
entire output.
Yes, and this happens because the y in linear regression based. Okay, so this is called least square classifier. So the y in least square classifier is just w transpose x plus b, or w transpose x plus w0, right? So there is nothing constraining the model to produce values between 0 to 1. So as a next step, we will see how to constrain the model to produce only 0 to 1, hopefully by the end of this lecture.
Okay, thank you.
Okay, so let us continue. So now we are going to switch gears and look at a different type of machine learning problem. Okay, so far we have seen regression, in which case you have x comma y, where y belongs to some real value, right? And we have seen classification, where you have x comma y, where y belongs to some categories, right? Okay, so now we are going to look at another problem. Okay, so I will introduce a new problem, which is the problem of dimensionality reduction. Okay, First, let me define the problem and then motivate why this is important. Okay. So now let's consider that I have some X, which is d-dimensional. Let X belonging to Rd be a random vector. Okay. So the problem statement is we wish to find k less than d directions. I want to find some k directions, okay, that captures as much as possible of the variance of X. Okay, so given, let's say, 100-dimensional X, I'm interested in finding some 10 dimensions, let's say. So I want to project this data from 100 dimension to 10 dimension in such a way that it captures as much as possible all the variance of X. Okay, so there are two questions like here. Like the first question is like, why is this useful? Like, so what is the application for this problem? Okay, so the question is D the number of features? Yes, D is the number of features. Okay, so now what are the applications? So first application that one could think of is feature extraction. Okay, so remember that like when you have more features than the examples, you have overfitting, right? Like so, and like in your assignment, like you are trying to like move, fill, like reduce the number of features by using L1 or L2, right? So now this is another way for feature extraction. Like you can actually take 100-dimensional data and project it to 10-dimensional data, right? Like to 10 dimensions, and like now you have lesser number of features. So you could do feature extraction. And another application for this problem is you could actually use this problem to do data visualization. Okay, so for example, if you have 100-dimensional data, how can you visualize this data, right? So 1D is fine, 2D is fine, even 3D is fine. So how do you visualize 100-dimensional data? So now, if I have an algorithm which will take this 100-dimensional data and actually project it to a 2-dimensional space such that the data structure and the variance is preserved, then this is a proxy visualization for this data, right? Like I cannot visualize the 100-dimensional data, but instead of that, like I can actually visualize it in the 2D space. Okay, so there's a question about variance. That would be my second part. I will discuss about like why I want to capture the variance very soon. Okay, so then the third potential application is actually some sort of lossy data compression. Let's say you have a lot of dimensions in your data, you want to compress it, and you are okay with some loss in information. Then you could do lossy data compression by using this dimensionality reduction. Okay, because remember that when you're projecting from high dimension to low dimension, like you are going to lose some information, right? That is unavoidable. And in that case, like you have a lossy data compression. Okay, so these are some applications. There could be many other applications. Okay, having motivated the problem, let's go back to the problem and see specifically why I designed the problem in such a way that I want to capture maximum possible variance of X. Okay, so I will repeat the problem statement again. So let's say I have some X which belongs to R power D, right? We wish to find K directions where K is less than D that captures as much as possible of the variance of X. Okay, so now there's a question, why should I care, like what do I mean by variance of X? It is just the regular variance of the random distribution that you have. Okay, so now the question is, why should I capture the variance, right? Like, so can anyone raise hand and answer, like why should I care about capturing the variance? Marcel?
Actually, mean is not median, and mean is not really important. Just the variance is important. We can shift the classifier up, down, left, right, but it doesn't matter.
Yeah, so variance is the most important statistics that we want to capture, right? Like, so because we like our classifier is going to be dependent on the variance in your data, right? So yeah, so that is why like we are going to consider the variance of X. Okay, so now, okay, so now we are going to discuss a couple of algorithms to do this. Like, let's start with a very simple case. Like, we're going to consider a 1D case. Okay, maybe before I start with the 1D case, a quick reminder that if you have noticed the schedule, there is no reading for this week, simply to give you more time to finish the previous week's readings. So, so for example, like in today's lecture, like, so we will be using the spectral decomposition of matrices, and that was your previous reading or the week before, right? Like, so if you don't do your readings, like, then like sometimes like you might see some concepts which are completely new to you. So if you haven't done all the reading before, I would encourage you to finish those readings this week. Okay, so let's start with the simple 1D case. Okay, so now the 1D case is find the single most important direction. Okay, find a single direction that captures as much as possible of the variance of X. Okay, so instead of saying k dimensions, like I'm just asking for a single dimension. Okay, so now let's make it more formal. So formally, we want some p which belongs to r power d. Okay, so this is the direction. We want some p, okay, such that the norm of the p is equal to 1, so as to maximize variance of P transpose X. I take the data X, I project it into this one dimension P, right? So it's P transpose X. I want to maximize the variance of this projection. Okay. Now, can anyone tell me why the norm of the P should be 1? So why P should be 1? Is there a hand raise?
Otherwise, your optimization problem is unbounded. You can increase P to whatever value n.
Yes. So if you don't bound the value of P, you could just keep on increasing the P, right? So you can basically, you can maximize the variance by letting norm of the P tending to infinity, right? So we don't want this case to happen. So that's why we're going to like bound the norm, like basically say that like the norm of P should be 1. Okay. Okay. So now let mu be the mean of the data, expectation of X. Okay. And let S be the covariance of the data. Okay. Now the covariance is defined by expected value of X minus mu transpose. Right. Now this is in the data space, right? So let me actually cut this so that we can compare it with the projected space. Oh, sorry. Page. Okay, so now this is in the data space, right? So now let's say for any P belonging to R power D, the projection P transpose of X, right? So it has the mean of, what is the mean of the projection? It is basically expected value of P transpose X, right? So expected value of P transpose X is basically P transpose expected value of X, linearity of expectation. So the expected value of X is given by mu. Okay. Similarly, the variance of P transpose X is given by expected value of P transpose X minus P transpose mu the whole square. Right? It's X minus mu the whole square. So in the projected space, right? I could actually write this as expected value of P transpose X minus mu transpose P. Okay. Now this is given by, you take the P transpose out. So what is expected X minus mu transpose is essentially the covariance of the data and P. Is that clear? Okay. So now our goal can be mathematically written as, I want to maximize the projected variance, right? So I want to maximize P transpose as P such that P is equal to 1. Okay. So probably I will do this maximization step after the break. So we will take a short break, but before that, I want to summarize what we have done so far. So like we have started with dimensionality reduction, which is the problem of taking a d-dimensional data and projecting it into some k-dimensional subspace, right? And it has many applications. And like before even considering projecting into a k-dimensional subspace, we asked this simple question, which is basically, can I take the data and project it into just one direction, which captures as much variance as possible, right? So, or in other words, we want to maximize the variance of the projected X, P transpose X. We can easily cheat by just increasing the value of P. So we set norm of P is equal to 1, right? Okay, so now this is the expected value of X is mu, covariance of X is yes, okay? And in that case, if I project the data, then the mean and variance in the projected space is given by the P transpose mu and P transpose SP, right? So we have kind of reformulated our problem as maximize the covariance in the projected space, which is P transpose SP, such that norm of P is equal to 1. Okay, so we will take a short break and we will start in 10 minutes when we will solve this problem. Okay, maybe it's a bad place to stop, but it's okay. I will stop the recording.